In this video, we're going to take a look at two examples related to rates of change. And before we get into the rates of change, let's just remember what our velocity functions represent. So when we think about our velocity functions, we have our position function, which is represented as generally s sub t. So if you're thinking about the position of a rocket, as I throw it off of as it takes off of a cliff, or if it's the position of a basketball as I throw it to a hoop, that has to do with the height in essence. That's what I'm kind of thinking about when we're talking about the position of our object. Then we have the velocity. Velocity, we've said, is the derivative of our position function. We can represent the magnitude or speed of that object, that we're discussing, by taking the absolute value of the velocity. So speed is really just the absolute value of our velocity. And then the last velocity type function we have is acceleration. Acceleration is the derivative of velocity, and therefore it would be the second derivative of the position function that we started with. And all of these are functions with respect to time. Now, once we understand our velocity functions, we want to talk about these rates of change. We have two rates of change that we're going to look at. The first one would be the average velocity. Average velocity is dealing with the position function. And when we are thinking of that, we have this average change. In other words, it's the change of the position divided by the change of time. So delta S means, delta means change. So the change of our position function divided by the change in that time frame. That's how we think about average velocity. Instantaneous velocity is simply the derivative of that position function at that time that we're thinking. So let's look at the first example here. In this first example, we are looking at a figure here. This is a graph that shows the position function of an airliner on an out and back trip from Seattle to Minneapolis. And they leave Seattle at 6 a.m. and return back to Seattle 8.5 hours later at 2:30 p.m. Now, we don't know what the actual value of this function is, but I can tell some information just based on the graph. I know that we are starting here at the leftmost point at the origin. This is Seattle, and as I am moving away, I'm flying, of course, over here to Minneapolis, then I am traveling some distance with respect to time. Here I am constant, so my position is not changing. It's still staying up here at the same location. And then we are decreasing in our distance away from Seattle because we're returning back to Seattle from Minneapolis. So from this, we can answer a couple of questions. The first question says, I want to calculate the average velocity of the airliner during the first 1.5 hours of its trip. In other words, what is the average velocity when time is between 0 and 1.5? So over here on the graph, we have 0 and 1.5, which is about right here at 600. So I want to know, what is the average distance here? Remember, average distance is going to be basically the slope of the secant line, right? So if I was to connect these two positions here, those two dots, then I could connect it using a secant line. So for our average velocity, we're going to take the change in our y values over the change in our x values, right? It's going to be the change. So it would be the value of the position function at 1.5 minus the value of the position function at 0 divided by that time 1.5 minus the time of 0. So when the function is at 1.5, a time of 1.5, when the time is 1.5, the function is at 600, I should say. So 600 minus, when time is 0, the function is at 0. all over 1.5. And that gives me a 400 miles per hour, or yes, 400 miles per hour velocity. That's the average velocity from time 0, 1.5 hours into the flight, in other words. Now, the next question says, okay, well, what's the average velocity between 1:30 and 2:30 p.m.? Or in other words, between a time of 7.5 and 8.5. So if I come over here to the graph and I locate 7.5, which is about right there, and 8.5, which is at the end, we can again think about average velocity would be the slope of the secant line passing through those 2 points. So average velocity would be the value of the function at 8.5 minus the value of the function at 7.5 over the difference in those times, 8.5 minus 7.5. So when time is 8.5, the position of the plane would be at 0. And when time is 7.5, the position of the plane is around 300, a distance of 300 away from Seattle. And then 8.5 minus 7.5 would be 1, so we would have a negative velocity of negative 300 miles per hour. Now remember, velocity is a vector, and so it can be both positive and negative. And in this instance, we're taking velocity to be positive as we fly away from Seattle, and it becomes negative then as we return back to Seattle. So it's just a position vector. The next thing we're going to answer here has to do with what time is it when the velocity is equal to 0. So remember that when the velocity is equal to 0, the plane, in essence, is just sitting still, right? When the velocity is equal to 0, the line tangent to the function would also be horizontal, right? Because the slope of that tangent line would be 0. So here we can see that the plane's position would be constant. So we are here and here. There is, in essence, no movement. There is no change in the position of the plane. And that's occurring if we left at 6 a.m. Then this would be about, that's roughly 9 a.m. And then this is 11 a.m. Okay, so it's a little shy of 9 a.m. and it's a little past 11 a.m. So we're going to call that 8:45 to 11:15, where if you think about this, we flew from Seattle to Minneapolis. You're sitting at the gate, and then you're going to fly back. So you're sitting at the gate would be probably the reason for that constant position. And then finally, the question we want to look at here says, okay, well, determine what the velocity is when at noon. What is the instantaneous velocity? That's what we're looking for at that point. What is the instantaneous velocity when time is equal to 6? So if we come over here to our graph and we locate 6 on our position function, we want to know what is the velocity at a particular point in time, which is related to our tangent function. So I'm going to draw a line here, and that's roughly tangent at the point. And it's kind of tangent. We're going to make it work because it makes our slope a little bit easier. I want to know what is the slope of this line at that point, in other words, right? So the slope of this point here is going to be the change in our y values over the change in our x values. And we know that this slope is negative, by the way. but I could say 1600 minus 800 divided by 5 minus 7, or in other words, that would be negative 800, or 800 over negative 2, or a negative 400 miles per hour. So at 6 hours, if someone were able to clock the plane flying back from Minneapolis to Seattle, then they would say, okay, right at that instant of 6 hours, the plane was traveling at 400 miles per hour on its return trip to Seattle.